Today, I want to talk about panel data models. If you don't know about them, this will be fun. If you do, maybe a nice reminder of why I think they're really awesome. In particular, I'm going to talk about fixed effects panel data models. So let's get into it. All right, so what is panel data? What is meant by panel data? Well, panel data is essentially a data set made up of multiple time series. So for example, you can see my little sample here. We have a time series for this individual named John, and we have a time series for this individual named Jane, multiple time series. The key element to identify panel data is the various individuals or entities being measured through time. So you have John being measured through time 1, 2, 3, 4, Jane being measured through time 1, 2, 3. And the panel data models are meant to fit linear models to this type of data, to fit to the panel data. So in this presentation, I'm going to focus on what that's like and the power of the fixed effects models. So really the goal for panel data models is to approach a better estimate of inference. So we're talking approaching causal inference. This is why people who are economists really like this type of model. It's taught in econometrics courses, for example. Not really used for predictive power, but for like prediction, but it could be, right? They're linear models, so they're simple and easy to understand, very interpretable. And I argue they are the best multi-entity time series inference models. And if you disagree, we can fight. No. All right, so let's walk through some of the math to demonstrate not only the simplicity, but the power of these models. And let's take a look here at your basic linear model setup. You have your outcome y, you have beta, the coefficient. You have your variables stuck in x, and we have this big thing that I call e, which is essentially the error, right? Well, we can think of the error as being built up of multiple parts. Okay, we got an alpha, a v, and an epsilon here. So the alpha we'll call the time invariant error. The v we'll call the time variant, and the epsilon is called the idiosyncratic error. So more specifically, these two errors right here theoretically can be solved because they're mostly just due to omitted variable bias. So theoretically, if we knew or had all of the variables we needed, we could account for that in our model and get a better estimate of our coefficient. The idiosyncratic error, on the other hand, is kind of any error that's just left over in the sake of real world examples like measurement error, just randomness that you can't get rid of no matter what. So as we focus on these, let's consider a dummy variable model. So this top one right here, I labeled it the dummy because it's just a basic linear model, but let's suppose that we're including a dummy variable for each individual entity in the data. So that is, we have a variable that tells us if we're looking at John or Jane, if you think back to my example. And so now let's demean this model and manipulate it. We can subtract some things from both sides, and that won't actually change the model itself. So if we subtract y bar here, let's walk through manipulation. So there's subtracting y bar, and now let's take a closer look at what y bar actually is. It's what you would expect. We're taking the average through time. So 1 over t times the sum of that variable through time. We do this to both sides of our original equation. We can distribute that through thanks to the linearity of this. And we get something right here you'll notice is that our time invariant alpha here is just going to be 1 over t times alpha I because it doesn't change through time. So we're just getting t times that. And of course, that cancels out. And now we know what y bar is. Let's go ahead and plug that back into our demeaned equation that we're working with. And we'll just substitute that directly in right here. And we can distribute through the negative sign, rearrange the terms, and what's that? We have a plus alpha I and a minus alpha I. Those, of course, cancel out. And that is how we get to what is called the fixed effects panel data model, which is quite nice and is completely equivalent to our original dummy model. As we have just shown, we just demonstrated that these are the same. Our coefficients will be the same. So let's talk about why this is so important and what some of these advantages are. Well, first off, in this model, we are controlling, in this setup, we can control for all time invariant factors. That alpha I canceled out. So that means we can implicitly control for anything that doesn't vary with time, such as race, gender, height, blood type, genetics, eye color, language, birth order, date of birth, parental education, skill, talent, and much, much more. Very powerful indeed. And it's also computationally very inexpensive. So compare this to fitting a new dummy column for each individual. So if you can imagine, if we have like 1 million or millions of people in a giant panel data setup, the computation explodes, right? Because the computationally speaking, right, it widens the data set to create essentially a dummy variable for each individual when it's doing that computation. So in a lot of cases, you can't actually do it, but with this, you can. And we have packages such as panel OLS in Python or PLM in R that allow this to be done quite easily. But here's the nice thing. You can apply this transformation on any linear model you want and get that same benefit. So it's not all good, right? There's some limitations as always. So what does this lack? Well, for one, the most obvious would be that it doesn't control automatically for time variant effects. If you want to control for things that vary with time, those have to be explicitly put in the model. So we kind of got half of our problem taken care of, and we're approaching at least better estimates of actual causal effects, but it doesn't take care of everything. There are, of course, assumptions with linear models. I think a lot of those can be mitigated if you're careful with the standard error approach that you're using. If we use in panel fixed effects models, you can use a robust clustered standard errors, which can help mitigate those. But still, that's something to consider. And of course, the data has to be set up for this, right? You need multiple observations per each entity, so certain data sets just wouldn't really apply for this type of model. And I argue that it's not the most ideal for prediction. If prediction is your goal, you can use more powerful nonlinear approaches if you don't care about the interpretation of it, for example. So I look at this as a really, really awesome inference modeling approach, and one that frankly is underutilized. And lastly, there is some limited packaging support, especially in Python, but that's not a huge deal. What this really means is that if you're going to be doing this, you kind of have to apply some of these transforms on your own. I did mention the panel OLS, which comes from stats models packages, one of those libraries from Python. But if you're going to apply this in other settings or like on a logistic regression, for example, that's not built in, but easily can be applied to logistic regressions, given that it's a linear model. So you'd have to do that transformation on your own. Anyway, that is panel data fixed effects models. Something to keep in mind as a powerful tool when it comes to inference when you have a multiple time series data set. And I yield my time.